Also, for all the associative containers and the hash table containers, what the asterisks here on all these yeses imply is that you do not specify a position, that is an iterator, where the insertion is supposed to occur, because the associative containers and the unordered containers maintain their own internal structure about where things are supposed to go. So you can insert a value without specifying where that value is supposed to go, and so forth. Also, just as a matter of historical inconsistency, whereas we would use remove to remove a value from a list or a forward list, it turns out we use erase instead of remove for the associative containers and the unordered containers. A lot of effort has been put into trying to keep these interfaces and member functions as similar as possible, but here we've fallen short of perfect. On slides 61 and 62, we have example code making use of the assign, insert, remove, and erase facilities. And then on slide 63, we have the output produced by that code on slides 61 and 62. So let's walk through this example. Here we have a vector of int v11 initialized with 135, and then in place of the original contents of v11, I'm going to assign new contents. Notice that this version of assign takes an initialization list, that is, a sequence of values contained in curly braces and separated with commas. So after this assign, v11 will contain that sequence of 11 int values. Into the list of int li1, as initial values, I'm providing a subrange from v11. Since a vector of int has random access iterators, I can use addition and subtraction of ints with my iterators. v11.begin plus 1 is going to be an iterator 1 past the initial element of v11, so that's going to be an iterator for the 2. And v11.end minus 1 is going to be an iterator for the 6. That is, for the last element in v11. Now recall that if I construct a container specifying a beginning iterator and an ending iterator, then everything from the beginning iterator up to but not including the ending iterator is included. So in this case, what's going to be included is everything from the 2 up to but not including the 6. All right? Here in this black range for loop, I'm displaying v11, that's this first line of output, and then in this blue range for loop immediately below it, we're displaying the contents of li1, which is this subrange of what's in v11. Remove for a list or for a forward list can be given a value as an argument, and the list will be traversed. Any occurrences of that value will be removed from the list. So in the case of li1, these 3 zeros are going to be removed from the list. So the list contains 246824. Notice here I'm declaring an iterator, it2, initialized with li1.begin. Now a list does not have random access iterators, but it does have forward iterators, and so I can increment my iterator once and twice to move the iterator ahead 2 positions. Okay, so when the iterator was at begin, the iterator was at the 2, and when I move it forward 2 positions, the iterator is, quote, pointing at, unquote, the 6. Consequently, when I say li1.erase whatever is at that iterator it2, that's going to erase the 6. And so now, in this red range for loop, when I display the contents of li1, I'm going to just have 24824. That is the 3 zeros were removed by the remove member function, and the 6 was removed by the erase member function after I had started my iterator at the beginning and incremented forward 2 times. The next thing I'm doing here is I'm inserting into V11, starting at the location V11.begin plus 2, that is, V11 contains 02468. V11.begin plus 2 is therefore, quote, pointing at, unquote, the 4. So I'm inserting ahead of the 4 the entire contents of li1. That is, everything from li1.begin up to but not including li1.end. And sure enough, we see here the values in li1 inserted ahead of the 4, so that when I display vi11 in this green range for loop, I get out vi11 modified with the contents of li1 inserted ahead of the first 4. Finally, here on slide 62, I'm creating a multiset of int msi. Initially, msi is empty. Then I'm doing an insert into msi the entire sequence of values in the vector v11 from the beginning up to but not including the end. When I display msi in this black range for loop, the elements of msi are the same as the elements of v11, except that a set, in this case a multiset, stores elements by default in ascending order. So I have 4 zeros, 4 2s, 4 4s, 2 6s, and 2 8s. Now, if I, from MSI, erase 0 and erase 6, that's going to erase all the zeros and all the 6s from MSI. So when I display MSI again in this blue range for loop, the 4 zeros and the 2 6s have in fact been erased. Into MSI, I can insert a specific collection of values by using the initialization list notation. Here I'm inserting 5 negative integer values. And I can also insert one value. Here I'm inserting a 7. So now, when I use yet another range for loop to display MSI again, what I see is that all of the negative values have ended up in ascending order ahead of the positive 2, and the 7 has been correctly inserted between the 4 and the 8. So I still have this collection of values in ascending order. Finally, di here is a deck of int. Notice that I'm initializing di by using reverse iterators on MSI. So what's going to go into the deck di is all the values in MSI starting from the reverse beginning, that is, starting from the last value stored in MSI, to but not including the reverse end. And recall that the reverse end is just prior to the first element in MSI. So if we look at the display of di produced by this green range for loop, you'll see that it has exactly the same values as MSI in exactly the reverse order. So how to summarize? This seems like just a giant catalog of stuff. It's a bit hard to get a handle on all of it, but it's extraordinarily important to try to get a handle on as much of it as you can, because what the standard library containers and iterators provide is virtually all of the standard data structures used in applications, with mechanisms for initializing, modifying, erasing from, and traversing through the contents of all of these data structures. These are extremely useful examples of what's called generic programming. All of these containers are generic. They can contain any kind of copyable data. The iterators are generic. They can be used to, quote, point to, unquote, any type of element that can go into one of the containers. And when we combine these things with algorithms, you'll see that we have tremendous power to store and manipulate almost any kind of data in almost any way that you can think of.